Yes, then we're very happy to have you here again Ingo, today for the second part of the lecture on deep inelastic scattering. I'm not going to say deeply again, after learning or remembering studying that it is actually deep and inelastic. So looking forward to the second part of the lecture.
Okay, thank you everybody. I will share my screen. So good morning everybody, and so we will attack the second lecture on deep inelastic scattering. And so yesterday we covered aspects of deep inelastic scattering just based on basic symmetries of the theory. Why are the slides? There shouldn't be a slideshow. Okay. No.
You might have to go on pause or pause.
I need to go to pause.
So if you do this full screen, then it had play on. Now you go to play on.
Okay. Yes, right. So yesterday we covered aspects of deep inelastic scattering just based on basic symmetry principles of the theory, and today we will now discuss it in the context of the Parton model, basically. So so let's have a look. So the Parton model was introduced by Feynman in the late 60s, probably also triggered by the experimental results, by the SLAC collaboration, which found that the structure functions are scaling in the and do not fall off steeply with increasing Q square, what was initially thought. So the historical Parton model then describes the nucleon as a collection of point-like constituents called partons instead of a mushy nucleon with a small core and then a cloud of pions. Instead, it's a bag of a collection of point-like constituents. And today, of course, the partons are understood to be identical with the quarks postulated by Gell-Mann. And kinematically, at high momentum, in a so-called infinite momentum frame, the partons can be considered as free. And then the interaction of one parton with the electron does not affect the other partons, and this leads to scaling in Bjorken X, as we will see below. And so in an infinite momentum frame, the proton is moving very fast, so that for momentum is given by the energy, 0, 0, the energy, and the energy is much bigger than the proton mass. And then the quark parton is moving parallel with the proton, carrying a fraction psi of its momentum. Okay, as we will see later today, the naive Parton model is of course replaced by QCD factorization theorems, but the basic kinematic picture remains of course important and relevant. So here's a graphical presentation of electron protons deep inelastic scattering. And in the Parton model, we rather get a diagram like this, where we pick a parton out of the proton, which carries a momentum fraction psi of the proton, and then does an elastic scattering with the electron. So here we have a cross section, the sigma hat of elastic electron parton scattering, where the parton is really point-like. And then to connect the hadron level cross section with this partonic cross section, we need to multiply it with the probability or the number density of partons of type I carrying a momentum fraction of the proton in the interval xi plus d xi. And then we have to sum over all possible partonic processes to get this hadron level cross section. And the word incoherent means that we really, for each Platonic cross section, we sum the cross sections and not amplitudes. So there are no coherence effects between different Platonic processes. One can also do the same at the level of the hadronic tensor. So if we, so to say, square those diagrams here and strip off the leptonic part on the top, we find on the left the hadronic tensor, graphically represented, and on the right in the parton model, where again we pick out here a parton with momentum fraction psi, which goes out and goes back in here. So the upper part is then the analog of the hadronic tensor, a Platonic tensor, and the lower part is actually then a graphical representation of the parton distribution I. And this parton distribution is not calculable, but is always the same, independent of the process on the top. So it's universal. And then the Platonic tensor, on the other hand, is calculable with our Feynman rules for QCD and QED. At leading order, it's infrared safe, but at higher orders, it's not infrared safe, and one needs to remove certain collinear divergences to get here an infrared safe expression. But that is then part of the QCD factorization theorems, which go beyond this naive parton model, which does not include any QCD corrections. So as a formula, the hadronic tensor is then given as a convolution integral of the Platonic tensor with the parton density. So that are two views which both can be used and can be useful. So which partons do we have? So as I said, it is tempting to identify the partons with the quarks of Gell-Mann's quark model. And then the proton consists of 3 valence quark, as we know, 2 up quarks, 1 down quark, which carry the quantum numbers of the proton, so the electric charge, the baryon number. And so naively, then you could say, okay, there's an up quark distribution of X, and each of these 3 quarks carries 1/3 of the proton momentum. So it's delta X minus 1/3, and a factor of 2 because we have 2 up quarks. And then one can calculate quark number sum rules by integrating over these distributions, and we find that this integral for the up quark gives 2, for the down quark 1, for a strange quark it would give 0. And we can look at the quark momentum sum rule if we calculate the integral x times q. Then we find the momentum fraction carried by the quark. So the up quark will carry 2/3 of the momentum, and the down quark will carry 1/3. So in reality, of course, the valence quarks are bound together by gluons, which will lead to a smearing of the delta distribution. And in addition, the gluons can fluctuate into a sea of quark anti-quark pairs. So that you can see. So the delta distribution in the lower figure gets smeared, and this rise on the left, this indicates the sea, the quark sea due to gluon splitting. And then the up quark can then be described as a valence component plus the C component. And the same, the down quark is down valence plus the C. And the C is the same as U bar. So then there's a problem. Experimentally, it was found that the momentum fractions of the quarks do not add up to 1, but rather to 1/2 of the momentum of the proton. I mean, in more precisely, I think it adds up to 58% or so, but roughly 1/2. No? And that means that the gluon has to carry roughly the other half of the momentum, and it doesn't couple to the photons we had in the exchange. So we really have to include a gluon distribution as a parton in this model. So in summary, the following picture emerges. The proton consists of 3 valence quarks, which carry the quantum numbers of the proton. Then there's a sea of light quark anti-quark pairs, UU bar, DD bar, SS bar, when probed at a scale Q, which is much bigger than the mass of the quark. So if we probe the nucleon at a very high scale, then we have also a CC bar component, a charm, anti-charm component, and so on. And there's a gluon distribution which carries about 50%. So more precisely about 48.1% or something like this. And the quark number sum rules are then satisfied by the valence distributions. So the integral over U valence gives 2, over D valence gives 1, and there is no valence strange distribution. So the integral over S minus S bar has to give 0. And similarly for charm minus anti-charm and so on. And the momentum sum rule is then written down here. The sum over all fractions carried by the quarks, anti-quarks, and the gluon has to give 1. So all momentum fractions have to add up to 1. So now one can compute structure functions in the parton model. And there are basically 2 ways. So either we take the formula for the cross section, d sigma, in the parton model, which I usually do in my particle physics classes. But here, for a change, one can also use the Platonic Tensor and calculate this, and that's what we are going to do here. So the Platonic Tensor for a parton of type I is given here. So there are different components. It's the product of currents between Platonic states averaged over the spin. Then we have 2 pi 4 to the 4 a momentum conserving delta function. And then we integrate here over the phase space of the outgoing parton, P prime. Yeah, you may probably know that D4 P prime delta P prime squared is the same as D3 P prime over 2 times the energy. And the 2 pi cancels 1 of the 2 pi to the 4 factor. So you can write this also as D3 P prime over 2 pi to the 3rd, 2 times the energy. So the usual phase space element for an outgoing particle. So then let's evaluate the D4 P prime. So we use the delta function here to make this integral trivial. And then we get that a factor 2 pi. And the delta function P prime squared becomes this delta psi P plus Q squared. So now one can evaluate this average matrix element of currents. And that is now, that we know how to do, because now we have a current for point-like fermions S and QD. So we know that this gives us the typical trace of with Dirac gamma matrices and the couplings, the electromagnetic charges which are present in the currents. So then one can further evaluate this delta function by just evaluating the square. That gives then delta 2 psi pq plus q square. And that can be brought into the form 1 over 2 pq delta psi minus x. Then the trace is calculated with the usual trace methods. And you find that this trace is 4 times this expression here in the bracket. So I had forgotten a factor 2, which I have added now by hand. And this expression inside the bracket can be rewritten in this form. Sorry, some indices got lost here. So this should be a mu, an upper index mu, and this should be a g mu nu. but I think it should be clear. No? And then, as expected, for elliptic scattering, we get a delta function of 1 minus x hat, where x hat is the Platonic equivalent of the Bjorken x. So it's x divided by psi here. And then one can insert this piece into the convolution formula to find the standard expressions for the structure functions f1 and f2 in the Parton model. Whoop. Okay, so here we just calculated the Platonic tensor here, giving us this result. And then the Hadronic tensor is given by a convolution of this Platonic tensor with the Parton density. And the delta function here will make the convolution integral trivial, and you find the following structure functions. And f1 is given by 1/2 sum over the electric charges squared times the Parton density of x, and f2 is 2x times f1. So this model provides an explicit realization of Bjorken scaling. So there's no q-square dependence here due to the point-like partons and this. And then we also have there's a famous relation called the Canon-Gross relation, which tells us that f longitudinal, and as I said in the last lecture, f longitudinal is given by f2 minus f transverse, and the Canon-Gross relation tells us that f longitudinal is equal to 0, which in turn implies that f2 is 2x f1, so f2 equal f transverse. And this observation gives support to the fact that the partons are spin 1/2 fermions. In fact, if the partons were spin 0 particles, we would have found that f transverse is 0, and hence f2 would be equal to fl, which is an exercise on the following slide. So there are some puzzles to be addressed later. So the naive Parton model assumes that the partons are free, and how can this be true in a strongly bound state? And second, one would like to have a field theoretic description within the QCD of what is going on, including the effects of interactions and quantum fluctuations. So FL, the Canon-Gross relation tells us that the longitudinal structure function is 0. Here's again, here are data for FL from Zeus. And you see FL is not 0, but small. So, and in fact, FL is also non-zero in the calculation if you include quark masses, or if you include Z boson exchange, or if you include QCD corrections. So, but still, FL is very small, as predicted even by the naive Parton model. So, homework problem number 1. So, this leading order Parton, the leading order Parton model expressions for the structure function in electron proton scattering with photon exchange, and in neutrino proton scattering, assuming a diagonal CKM matrix and a 0 charm mass, are given here in the yellow box. And yeah, so you can quite easily verify this list. I mean, for the electromagnetic interaction, you have here the charges, the electric charges squared of the quarks, and then you basically have to look which partons can come in and interact with a photon. So there can be a U bar, CC bar, DD bar. And for example, with neutrino scattering, where you have a W boson, that's different. No, I mean, if you have a W plus, then you need an incoming down quark which interacts with a W plus to produce then an up quark. if we neglect the CKM matrix, we don't produce a charm quark from and down. And so you can think which quarks can come in, and there is no electric charge. We can think about weak couplings and verify these structure functions. And we need many different of these structure functions in order to disentangle the different flavors of the PDFs. So if we would just measure, for example, F2 electron proton, then we would always measure this combination of parton distributions, which makes it difficult to tell apart the up quark from the charm quark and from the down quark. But you see, the other structure functions have different combinations of parton densities. And if you combine them, then one can hope to extract really the up quark distribution and the down quark distribution and so on. So it's important to have different of these structure functions in an analysis of parton densities. And then the structure functions satisfy some rules which have been established often before the parton model, but they can be verified easily in the context of the parton model. So there's the Adler sum rule, that's the integral of F2 neutrino neutron minus F2 neutrino proton over 2x. If you integrate over it, that it gives 1. There's a Bjorken sum rule, which is written here, a Gross-Lulin-Smith sum rule for F3. The Gottfried sum rule, which predicts 1/3 if the up quark C is equal to the down quark C. And there's a famous relation that 5/18 F2 neutrino nucleon is quite similar to F2 electron nucleon. Okay, so it's a good exercise to work this out. What is really here on the right side. And experimentally, the Gottfried sum rule indeed gives a value which is smaller than 1/3, which then leads to the conclusion that the down quark C has to be bigger than the up quark C. So then another homework problem, as I said, if the partons were massless spin 0 particles, then we would use a vertex like this for a scalar particle coupling to a photon. The vertex would be given essentially by the 4 momenta times the couplings. And with this Fanon rule, you then can recalculate the Platonic tensor, and you should find a result like this, which then leads to the observation that F2 will be equal to FL and F transverse will be equal 0, in contradiction to the experimental result. So that's why the Kellen-Gross relation is FL equals 0 is really some experimental evidence that the partons have to have spin 1/2 and can be identified with the quarks. So far we have been discussing the naive parton model, and yeah, now we would like to discuss a little bit the caveats and the puzzles. So a nucleon at rest is a very complicated object, as you can see here. If you look at the graphical picture, I mean, there are lots of fluctuations at all space-time scales. So there can be some fluctuations which are at short distances, but there can be fluctuations which cover long distances and connect the different partons here. And so some of these fluctuations will clearly be long-lived compared to the time an external probe will participate in an interaction. So what you see during such a probe is a complicated picture. So clearly not free partons, but they are interacting with each other and so on. So short-lived fluctuations are not a problem. I mean, they will only lead to renormalizations of the masses and the couplings, but the long-lived fluctuations will prohibit a picture where you have a free parton that then interacts in a short distance process. So now, if we go to a high energy frame, we will have a dilation of all internal timescales. So for a high energy nucleon, so everything will get stretched. No? So now the interactions among constituents now take place over timescales that are longer than the characteristic timescale of the probe. So if you look at this blue blob, so essentially the constituents behave as if they were free. I mean, you see in addition maybe some other free gluons floating around, and this gluon, there could be fluctuations, so there could also be other quark lines in addition to the valence quark lines floating around. But essentially, the probability that during this interaction, the two quarks here, for example, are coupled by gluons, is this probability gets suppressed. And that is then the reason why kinematically one can hope to have interactions by free partons up to an error which is suppressed. So then, of course, proofs from first principles of QCD show indeed that the parts involving long and short time scales can be separated into independent factors. And that is then the result of the famous factorization theorems of QCD. So now that brings us a little bit to the PQCD formalism. Yeah, just to start, I mean, our starting point is, of course, QCD, quantum field theory for the strong interaction. And yeah, we have the well-known Lagrangian for QCD based on SO3 color gauge symmetry, renormalizability. And yeah, so our fundamental degrees of freedom are quarks and gluon fields. We have 7 free parameters, the gauge coupling, and the 6 quark masses. And then we know the properties that we need to explain confinement, so that we do not observe free quarks and gluons, but instead those objects are confined in color neutral hadrons of size about a Fermi, or in the final state that they hadronize into the observed hadrons in the detector. And also asymptotic freedom, that's the fact that the strong coupling becomes small at short distances, so that one can do perturbation series. So at short distances, quarks and gluons behave as free particles. Yeah, and so this asymptotic freedom is, of course, has led to a Nobel Prize due to the calculations by Gross and Wilczek, and independently Politzer. So the running coupling, taking into account quantum corrections, loop corrections to the gluon propagator, you find you need to renormalize. That leads to a scale dependence of the coupling constant and a differential equation which describes the scale dependence. So that's known as renormalization group equation. So the logarithmic derivative of AS, where I define AS as alpha S over 4 pi, is given by a beta function, which can be expanded in AS, and the leading term is minus beta 0 AS squared, and beta 0 is 11 third CA minus 2 third NF. CA is 3, and NF is the number of active flavors in the loops. So this beta 0 is positive, such that the entire beta function is negative. And that leads to asymptotic freedom, because if the right-hand side is negative, that means that AS has to become smaller if we increase mu. And that's what we see. And this equation can be easily solved by separating the variables. So putting the term with AS on the left side and the log of the mu square on the right side, you can just integrate this equation to find the solution for AS of mu. So for the PQCD formalism, there are two key ingredients then. First of all, there's asymptotic freedom, which tells us that PQCD, perturbation theory, is possible as long as all scales in the problem are hard. And hard scales are scales which are, say, above 1 giga-electron volt. So, or distances smaller than 0.2 Fermi. And factorization tells us then that it's possible to separate hard and soft scales. So the soft part is then universal, and the hard part is not universal but calculable, and that leads then to a formalism which has predictive power. So, and then all this is comprised in QCD factorization theorems, which have been really rigorously derived from first principles in QCD. So schematically, the cross-section can be calculated as a convolution of parton distribution functions with so-called short distance cross-sections or hard scattering cross-sections, plus an error which is suppressed by the hard scale, by some power of the hard scale. And the parton distributions are composed out of quarks and gluons, and describe, if you like, the structure of the proton as it is seen in high energy interactions. In addition, these factorization theorems provide field theoretic definitions of the PDFs, so that one can use these definitions also to try to calculate them, for example, on the lattice. And the PDFs are universal, that leads to predictive power. That is really a crucial aspect. If the parton distributions were not universal, and you could use them for one process, but not to make predictions for other processes. And then, of course, it's much less charming, the entire formalism. And the hard part is process dependent, but calculable in perturbation theory. And essentially, the hard part is a Platonic cross-section, which we know to calculate with our Feynman rules. But then one has to remove the long distance pieces which are still there, so the collinear divergences or the big collinear contributions via a procedure which is called mass factorization. So here would be, for the case of inclusive DIS, the factorization theorem. It's in principle the same formula as before in the naive parton model, but the difference is now you see the PDFs depend on factorization and renormalization scales. The Platonic tensor, the hard scattering tensor, if you like, depends also on the factorization scale, the renormalization scale, and alpha S, always here in the form of the ratio with respect to the hard scale. And the error of all this game is, it's inverse. It's lambda square over q square. So sorry, this is wrong. It has to be the inverse, lambda square over q square. So that if q square is big enough compared to some hadronic scale, this error gets suppressed and very small. And this formula for deep inelastic scattering, there are then similar formulae for other processes. For example, in hadronic collisions. So schematically, you would write the cross section at the hadron level as a convolution of a Platonic process, where you pick the parton A out of the upper proton and the parton B out of the lower proton, carrying momentum fractions psi1 and psi2. And then the universality, as I said, tells us that we can use the same PDFs in different processes. For example, deep inelastic scattering, the structure function F2 has such an expression in terms of the PDFs. The Drell-Yan process has another expression. Inclusive hadron production has another expression, where in addition you need a fragmentation function of the outgoing parton into the observed hadron, and so on. And if you combine all these observables in a global analysis, you can hope to disentangle the different parton flavors and then make predictions for your favorite new physics process. So this responds a little bit at the question for the recitation session yesterday, whether deep inelastic scattering is still cool. I mean, one motivation is certainly that you need them to make predictions for new physics processes, and this has become a precision game because we haven't observed anything. So if there is any new physics, say at the LHC, it will be in some tail. It will be a small signal hidden maybe in a big background. So you really need to understand the standard model background very precisely. You need to know the signal precisely if possible. And one source of uncertainty is, of course, the error due to the PDFs. So you need to know the parton distributions precisely. And one backbone of any parton distribution global analysis is, of course, deep inelastic scattering. So it's from this perspective, it's still very, very crucial. In addition, one may argue that there are still interesting there's still interesting stuff to learn about the hadron structure itself, in particular its upcoming electron-ion collider. So the conclusion from my side is yes, deep inelastic scattering is still very cool. So a word how to compute the hard scattering cross-section. So at leading order, it's just a Platonic cross-section. But at next to leading order, you have to remove long-distance parts via a procedure called collinear subtraction or mass factorization. As a result, then, these hard scattering cross-sections will depend on the factorization scheme. So you have to subtract the divergences, but you are free to subtract also finite parts, which is not unique. So it depends on the factorization scheme at the end. And the parton distributions will also depend on the same factorization scheme, so that the observable itself is independent of the scheme. Okay. So just to show you the diagrams, if you want to calculate the structure functions at next to leading order in deep inelastic scattering. So first of all, you have the leading order quark initiated diagram here. But at next to leading order, you have to include gluon emission from this diagram. So from the incoming quark, from the outgoing quark, and the corresponding virtual diagrams. But at next leading order, also a new channel opens up. So the boson-gluon fusion channel, where you have a photon and a gluon, which produces a quark-anti-quark pair. And yeah, as I said, when you calculate this, the real part will have soft divergence. The virtual part will also have a soft divergence, which cancel. And in addition, the real part here has a collinear divergence, and the virtual part too. And they have to be treated by mass factorization. And finally, the virtual part also has UV divergences, which will be treated by a procedure called renormalization. So here I have a couple of slides on the different divergences, but I will not go into it because Dave Soper discussed all this in great detail already. So I can be very quick on it. So I said there are UV divergences and infrared divergences. And the infrared divergences are split up into soft divergences and collinear divergences. And so as I said, UV divergences are treated by a procedure called renormalization that leads to the renormalization scale dependence of alpha S. Soft divergences, so for reasonable observables, real soft plus virtual soft is finite due to the KLN theorem. And the collinear divergences due to collinear branchings have to be treated by another procedure, which is very similar to renormalization. And this procedure is called mass factorization. Okay, so that's where the divergences come from. So the mass factorization is just a technical procedure how to get the hard scattering cross section from the Platonic cross section sigma tilde, which you calculate here. So the sigma tilde has already been renormalized. So it's already depending on mu r, but there are still the collinear divergences in. And then as for renormalization, where you have some multiplicative renormalization, you have some multiplicative factorization, just that the multiplication is a convolution interval. So there are two equations now. The hadron level cross section is a convolution of the, say, naive parton distributions with the Platonic cross sections, which are still not infrared safe. Then the Platonic cross section somehow can be written as a product, as a convolution of universal factorization constants, mass factorization constant, and a infrared safe short distance cross section. And then you take this formula and you plug it into the upper formula. And that is the equation here on the lowest line. So sigma is an F tilde times gamma times sigma hat. F tilde times gamma will be combined to give the, if you like, renormalized PDFs. So that the end result is then the convolution of the renormalized PDFs with the real hard scattering cross section. And these mass factorization constant gamma, they are known and calculable in perturbation theory. So for example, at next leading order, gamma would take the form alpha s 2 pi, the splitting function, 2 over epsilon in dimensional regularization, plus a finite part, which is in the MS-bar scheme, again given by the splitting function times this standard expression appearing in dimensional regularization. Euler gamma minus ln 4 pi plus ln mu f square over mu square. Okay, and then you can develop gamma perturbatively. The Platonic cross section can be developed. The short distance cross section can be developed, and then you can compare order by order the term, and you find that the leading short distance cross section is just a Platonic cross section. Then the first hard scattering cross section is, so then the next to leading order Platonic cross section minus this mass factorization procedure, and so on. So you can continue this to higher order systematically. So in deep inelastic scattering, the hard scattering cross sections are called Wilson coefficients, and then the parton model formula for F2 would look like the quark distribution convoluted with a Wilson coefficient C2 quark plus a gluon distribution convoluted with the Wilson coefficient C2 gluon, and so on. I mean, the only one thing you should note is you have F1 and you have 1 over x F2 and 1 over x FL, which are somehow on the same footing. So it's useful to compare, to take 1 over x F2, 1 over x FL for many of the discussions. And then the Wilson coefficients have an expansion in the perturbative, in the strong coupling. So the leading order Wilson coefficients for C2Q, we just calculated it in the parton model. It is just the quark charge squared times the delta function. Okay, and the other, there is no gluon process at lowest order, so the Wilson coefficient is just 0. CL is 0 for the quarks too, and so on. And then the higher order Wilson coefficients, of course, are really functions in Z which have a distribution part. So there are distributions like the delta distribution, but also plus distributions, but also regular finite functions in Z. And that can be calculated and has been calculated. Just to show you, I mean, the next to leading order calculations of the Wilson coefficients come from the late 70s. For example, the famous paper by Altarelli, Ellis Martinelli, or Fumansky-Petroncio, which have been used for a long time. But then now, in the meantime, there have been calculations of the Wilson coefficients at next to leading order and even next to leading order and so on. So they are all in the literature, and so one can calculate the structure functions to very high perturbative order. So let's have a look at at the parton evolution, probably as a last big topic. So as you can see here, the result of all this renormalization and mass factorization is that the PDFs depend on the factorization scale and the renormalization scale. So typically in deep inelastic scattering, we identify those scales with the virtuality of the photon. So mu f equal mu r equal q. And yeah, physical observables like the hadronic tensor, of course, do not depend on the scales and schemes. That means one has to use the same scheme here and the same scheme for the hard part, of course. And the remaining dependence on the scales is only due to missing higher orders. So if you would have the PDFs to all orders, the hard part to all orders, the observables would be independent of mu f and mu r, which is somehow our way to calculate. At finite orders, there is a residual dependence, and that's, as many of you probably know, is the reason why these missing higher orders are estimated by varying these scales around a central scale by some arbitrary procedure, but a procedure everybody is using, so one can somehow compare it. Yeah, first of all, as I said, we have the renormalization group equation for the strong coupling, known to very high orders in different schemes, in different renormalization schemes. And here you can then see even a figure how the running depends on the number of active flavors. So the short answer is, when you have more active flavors, the running slows down. If you just keep 3 flavors, alpha S falls faster. And when you switch on then 4 flavors, it's getting less steep, and 5 flavors, again, it's getting less steep, and with 6 flavor, again, the running slows a little bit down. And that's easy to understand because the absolute value of beta 0 becomes smaller when you increase NF. Or if NF is 16, beta 0 would even be negative, and we wouldn't have asymptotic freedom anymore. But unfortunately, we only have 6 flavors. So then we also have differential equations for the PDFs, again, that are renormalization group equations known as Altarelli-Parisi evolution equations. So one way to derive them is via this mass factorization procedure. I said before that the PDF is given by the bare PDF, even if this notion of a bare PDF is, of course, something what should avoid in a more complex formalism, but operationally it works in a procedure to get the right equations. So we have a bare PDF convoluted with these renormalization constants, which depend now on the scales. And then you can calculate the derivative with respect to the scale. and you find some equation which already resembles the Altarelli-Parisi evolution equation. The only catch is then at leading log. So here, initially, you still have the scale mu square, and you would like to have the scale mu f square. and here you can replace the f tilde by f, which is valid at the given order in alpha s, because f tilde is the same as f up to higher orders in alpha s. And then you somehow can have a hand-waving derivation of the Altarelli-Parisi evolution equations starting from this mass factorization formula. That's something you can find in the Tarsi lectures from 1989 by Page. So no matter how you derive it, at the end you have this Altarelli-Parisi evolution equation, which is a coupled system of integral differential equations, right? So you have for each parton flavor, so I covers really up to, how many parton flavors do we have? U bar, DD bar, SS bar, CC bar, BB bar, TT bar, and the gluon. So we have up to 13 parton flavors, depending on the energy scale. And here this convolution is, to make it precise, is this Mellin convolution, which is defined here in different ways. And the upper form is very useful to see that F convoluted with G is the same as G convoluted with F, so it's symmetric. And yeah, so this convolution enters here, and the splitting functions are somehow like, I would say in QCD, they are the equivalent of prime numbers in number theory, and they are calculated so far up to 3 loops. So at the leading order, splitting functions are then given here. So we have some group theoretic factors. TF is 1/2. CF is a Casimir factor in the fundamental representation. It's 4/3. And CA is a Casimir in the adjoint representation, which is 3. And then we have, for example, the splitting of a quark into a quark. So we have a quark which splits into a quark carrying a fraction x. And so that would, if you calculate this within a process, you find that the result is CF 1 plus x squared over 1 minus x without this plus distribution. So just the regular piece. And this is, of course, a problem. When x approaches 1, you get a divergence. But if you include the virtual contributions, you can also have a virtual diagram here, which means that x goes from 1 to 1, and combine it with this diagram, you get a plus distribution as the end result. And I will define the plus distribution on one of the following slides. Similarly, you can have a transition of a gluon to a quark with a momentum fraction x. Then you have a transition of a quark to a gluon, and that is just regular. One can interpret certain terms. So the 1/x term here can be associated to the C. And you have the transition of a gluon into a gluon carrying x, and the full splitting function is given here. So here the definition of the plus prescription. So most often you see it defined together with a help function under an integral. So this integral of f of x over 1 minus x plus is then defined as f of x minus f of 1 over 1 minus x, such that, and this has the consequence that if x approaches 1, this is now regular and you can integrate it. So you one exercise is often you don't have the integral from 0 to 1, but from some number a to 1, for example, a equal x. So that needs to be evaluated as a little exercise. And as another little exercise, you can show that the splitting function PQQ can also be written in this form. So where now it's really visible that the first part belongs to the gluon radiation and the second part to the virtual diagram. But there's another form which is useful for the splitting function, and that is a definition given, which you can find in the Appendix E in the book by Field, Applications of Perturbative QCD, where you find the plus distribution defined as a limiting procedure. And that actually comes closer to what you calculate. So you calculate the real diagram with some cutoff on the energy of the gluon. And then you have the virtual diagram, again, somehow regularized. And that are the contributions, how you would actually add them together. And then in the limit of beta to 0, you would get the plus distribution. And this form is useful in certain calculations when you want to calculate, for example, the convolution of two plus distributions. With this definition, you won't get far. But if you use this definition, you can actually evaluate it. Yeah, and then in the PGG, so this delta function distribution comes from those two diagrams. One is the gluon loop, which goes with the color factor CA. If you calculate this, this gives you the Casimir in the adjoint representation. And here you have the color factor TF, which is just the normalization of the trace of the generators, which you find when you calculate such a fermion loop. And NF is then just the number of loops that you include. And that has to be added to the PGG. And then there are just many homework exercises you can do to familiarize yourself. So obviously here, from the symmetry of the diagram, a PGQ, so a quark splitting into gluon carrying a fraction x, is symmetric to PQQ with 1 minus x. And that you can then verify. And for the regular part, if you don't have the virtual diagram for PQQ, you find also PGG is of x is equal PGG of 1 minus x. So if you just take the regular part of this diagram here. Then it's sometimes interesting to know the splitting functions in the limit x to 1, in the soft limit. And so that are relations you can verify. Then you have conservation rules, which lead to rules for the splitting function. For example, if you take the conservation of momentum fraction, you really take the Altarelli-Parisi equation for this integral. You find rules for the splitting function, that the integral over PQQ plus PGQ has to be 0, and here another relation, and here a third relation, which has to be satisfied by the splitting functions. Oh, again, I leave this as an homework exercise. And I think this brings us also to the end of the lecture. Are there any questions? I mean, I will be around this evening also if you need to digest a little bit and start calculating something and have questions also. Or if you have a busy day, if you start calculating some exercises later and you have questions, then you can send me an email anytime and I try to answer it. It doesn't have to be for this evening.
Perfect. Yes, I also don't see any questions in the chat at the moment, but I'm sure once everyone starts to calculate and verify those identities or symmetries, then questions will pop up, and let's see whether we can discuss already some of those tonight in the recitation sessions. Thank you very much, Ingo, for this very good overview of the deep inelastic scattering process and its QCD implications and applications. And we will take half an hour of a break now, and then we will continue with another process which has a lot of implications and applications of QCD, namely vector boson production. And thanks again, Ingo, for your 2 lectures.
Yeah, thank you.
All right, see you everyone else in half an hour.